Hey, in this video, it's a little follow-on from our enzyme introduction video. So this is like enzymes part 2, and we're going to be going through all of the different factors that can affect the rate of an enzyme-controlled reaction. So stay tuned if you want to learn more about temperature, pH, enzyme concentration, substrate concentration, and both types of inhibitors. Now, the first one we're going to look at is temperature, which is one that you did at GCSE. So if we draw the shape of the graph, in fact, I need to label the axes first, don't I? So on the x-axis, which is the one that goes across at the bottom, I'm going to put temperature. Okay, so temperature is increasing. And on this axis, I'm going to put rate of reaction. And this is obviously our y-axis that goes up high. The graph would look something like this, yeah? And you've got like your fastest rate of reaction here. So this would be our optimum temperature, which is the temperature that the enzymes work best at, or the rate of reaction will be fastest at. And then either side of that, you can see as you approach the optimum temperature, so as you increase the temperature here, the rate of reaction is increasing up to the optimum temperature where you've got your fastest rate of reaction. And then beyond optimum, if you continue to increase the temperature, the rate of reaction is going to decrease quite rapidly, and it can fall all the way to zero rate, so no reaction at very high temperatures. So let's try and explain why this is. Let's start with this side because this is the easiest side, where you go above the optimum temperature. Obviously, above optimum temperature, enzymes will start to denature. Okay, and we went through this in the last video, but what that basically means is that the tertiary structure is lost. Okay, the bonds that hold the tertiary structure will start to break. So hydrogen bonds will start to break, ionic bonds will start to break, and the tertiary structure will be lost. The active site changes shape. And obviously what that means is it's no longer complementary to the substrate. And if it's no longer complementary to the substrate, then enzyme substrate complexes cannot form. And this is all linked to temperature, because as you increase the temperature and you increase the amount of thermal energy, the enzymes have more and more kinetic energy, and it gets to the point where they are moving too quickly, and those bonds that hold the tertiary structure together will break. Active site changes shape, no longer complementary to the substrate, enzyme substrate complexes cannot form. So we're using all of our key vocab in there. We've got tertiary structure, active site, complementary, and enzyme substrate complexes. Now, do remember that at low temperatures, enzymes are not denatured. At very low temperatures, the reason the rate of reaction is so low, so for example down here, is there's very little kinetic energy. So there's very little thermal energy, so there's very little kinetic energy. And if we've got very little thermal energy, very little kinetic energy, you're going to find that you have fewer successful collisions. Fewer successful collisions between the enzymes and their substrates. So with fewer successful collisions between enzyme and substrate, you have fewer enzyme substrate complexes forming, and therefore less product produced in a given time. Now you can see that as you increase the temperature here, the rate of reaction will increase, and we can explain that using the same language. So increasing the temperature means you increase the kinetic energy, and you will start to see more successful collisions between enzymes and substrates, and you will start to see more enzyme substrate complexes. Now, obviously, as you reach the optimum temperature, this is going to be the fastest rate of reaction, because the enzymes and substrates have got plenty of kinetic energy, you've got many successful collisions, you've got many enzyme substrate complexes forming, and then beyond that is where we start to talk about denaturing. So that's temperature. Let's have a look at pH. Now, pH can be a little bit different because different enzymes, even in the human body, have different optimum pHs. So, for example, we've got amylase in the mouth, which is in our saliva, which has an optimum pH of about 7. But in our stomach, we've got protease or peptidase enzymes that hydrolyze proteins, and they have an optimum pH that is very low of about 1.5. It's very acidic in the stomach due to hydrochloric acid. So you might see graphs with multiple curves. So you might see a graph like this, where the optimum pH is about 7, if we're talking about, say, amylase in the saliva, or you might even see a graph like this, where the optimum pH is much lower, maybe about 1.5 or 2, if we're talking about enzymes in our stomach. Now, again, we would describe these points as our optimum pH. Just put rate of reaction on there so you know what we're talking about, pH on the x-axis. Optimum pH, again, that is the best pH for that enzyme, so you'll get the fastest rate of reaction. Now, if you go away from that optimum pH, whether the pH is getting too low or too high, so you could label pHs that are too low or pHs that are too high, again, enzymes are going to start to denature, and we know what that means. It means that the tertiary structure is lost because the bonds that hold the tertiary structure together are breaking, like the hydrogen bonds. We know that means the active site will change shape. It will no longer be complementary to the substrate, and enzyme substrate complexes cannot form. And this is all to do with the concentration of hydrogen ions. Okay, because it's the concentration of hydrogen ions that determines the pH. If you increase the concentration of hydrogen ions, it makes the pH more acidic. And if you decrease the concentration of hydrogen ions, it makes the pH more alkali. And the concentration of hydrogen ions in the solution is going to interfere with the bonds that hold the tertiary structure together. So any change in the concentration of hydrogen ions away from the optimum pH is going to cause bonds holding the tertiary structure together. I'm just going to do my little number 3 there. Holding the tertiary structure together to break. Okay, so hydrogen bonds can break, ionic bonds can break. It's going to lead to denaturation of enzymes. And that's why the rate of reaction is going to decrease at pHs that are, we call them sometimes extreme pHs, any pH that is away from the optimum. And obviously, the further away from the optimum pH you get for that enzyme, the more bonds are going to break, the more enzymes are going to be denatured, and the rate of reaction is going to decrease. So that would be pH. Let's look at enzyme concentration. So if I put enzyme concentration on my x-axis and I put rate of reaction on my y-axis, I could do a line like this, okay? And it's pretty self-explanatory. It's the idea that if I increase the concentration of enzymes, I can increase the rate of reaction. And the reason for that is if I've got more enzymes, I've got more active sites. And if I've got more active sites, I can form more enzyme substrate complexes in a given time. It's kind of like having more workers in a factory, yeah? More people to do the job. Here, if I increase the concentration of enzyme, I've got more available active sites, which means more enzyme substrate complexes can form, and I'll get a faster rate of reaction. Now, in this graph, I am assuming, aren't I, that there is an excess of substrate. Let's just write that down and try and explain that a little bit more. So I'm saying here that if I keep increasing the enzyme concentration, I can keep increasing the rate of reaction. Now, I've drawn my line as if there's an excess of substrate. So if you keep adding more and more substrate, and there is always an excess of substrate available, then if you increase the enzyme concentration, you will keep increasing the rate. Now, obviously, if there's a limited amount of substrate, eventually the reaction will stop. So bear that in mind, because once all the substrate has been converted to product, the reaction is going to stop anyway. So there's no point keep adding more and more enzyme if you've got a limited amount of substrate. Once all the substrate has been converted to product, the reaction will stop naturally just because you've run out of substrate and it's the end of the reaction. So for this graph, I'm assuming that there is always an excess of substrate. We keep adding more and more. And in that case, the more enzymes, the faster the rate of reaction, because the more active sites are available and the more enzyme substrate complexes can be formed. Let's have a look at substrate concentration. So if I increase the substrate concentration in an enzyme controlled reaction, what is going to happen to the rate of reaction? Well, obviously, to begin with, as I increase the substrate concentration, there's more substrate available, more substrate to bind to the active sites and more enzyme substrate complexes. So as I increase the substrate concentration, I'm going to see an increased rate of reaction. But I'm going to draw my line leveling off or plateauing or starting to become constant, okay? Now, the reason for that, let's just explain it. There's going to reach a point where the number, or in fact, I'll say the concentration of enzyme becomes the limiting factor. Okay, so yes, to begin with, if I add more substrate, I'm going to see more enzyme substrate complexes and I'm going to see more product produced in a given time, which is increasing the rate. But the rate of increase is going to level off. Now, it's not leveling off because I'm running out of substrate, because I can see on my x-axis, I'm still adding more and more substrate. I'm still increasing the substrate concentration. So why is it leveling off? It's because the concentration of enzymes in this reaction is becoming the limiting factor. We can say that the active sites are all occupied. Or another way to say that is the active sites are saturated. So it's kind of like saying, look, there's no point keep adding more and more and more substrate because we've only got so many enzymes and all of these enzymes are working at their fastest rate. So at any one time, all of the enzymes' active sites are occupied or the enzymes are saturated by substrate. If we think again about my factory analogy, which I think is quite handy for this, it's like you keep adding more and more car parts and you want to make more and more cars in the car factory, but you've only got so many workers and they can only work so quickly. So there's no point keep adding more and more car parts and expecting to get more cars made unless you increase the number of workers available to make the cars. Okay, so the enzyme concentration is now limiting the rate of reaction. Unless we add more enzymes, the reaction cannot go any faster. If we did add more enzymes and we had more available active sites, we'd be able to increase the rate of reaction until the number of enzymes again became the limiting factor because all of the active sites are saturated by substrate. So that's our substrate concentration graph. Let's have a look at the last factor for A-level biology. Now, these are the inhibitors. Now, obviously, enzyme inhibitors, as the term suggests, are going to reduce the rate of reaction. Okay, so if there is an inhibitor present, it's going to reduce the rate of reaction. Now, this type of inhibitor that we can see here is called a competitive inhibitor. And the reason it's called a competitive inhibitor, as the name suggests, it's competing for the active site. Okay, now what that means is the substrate must be a similar shape to the inhibitor, or the inhibitor must be a similar shape to the substrate. And you can see that here. So here's the substrate, which is circular. Here's the inhibitor. Now, it's not the exact same shape because it is a different molecule, but it has a similar shape. And because it has a similar shape, it means it can bind to the active site. It has a similar shape to the substrate. We can say it's also complementary to the enzyme's active site. It can bind to the active site. So it's literally in competition with the substrate for the active site. And if the inhibitor binds to the active site instead of the substrate, we'll get an enzyme inhibitor complex forming instead of an enzyme substrate complex. So this is obviously going to reduce the rate of reaction because at any one time, enzymes are inhibited. Some of the enzymes will be bound to inhibitor instead of substrate, so you're going to get a reduced rate of reaction. Now, key things to remember for this type of inhibitor is if it's competitive, it must have a similar shape to the substrate. It must be complementary to the enzyme's active site. It is going to bind to the active site, and in doing so, it's going to prevent the substrate from binding and reduce the rate of reaction. Let's look at the second type of inhibitor. Now, this again is going to reduce the rate of reaction, but this is a non-competitive inhibitor. Now, as the name suggests, non-competitive, it's not in competition with the substrate, and it is not going to bind to the active site. Now, if we have a look at the diagram, you can see that the inhibitor is a very different shape to the substrate. So they are not similar shapes. But the way this works is the inhibitor binds to what we call an allosteric site or an alternative site on the enzyme. You don't have to use the word allosteric site. You can just say it binds to an alternative site. So just to be clear, it does not bind to the active site. It is not in competition with the substrate. It's not complementary to the active site because it's binding to an alternative site or an allosteric site somewhere else on that enzyme structure. So somewhere else in the tertiary structure. And you can see here, here's the active site that is complementary to the substrate. And you can see the allosteric site, or the alternative site that the inhibitor is binding to, is somewhere else altogether. But what's going to happen with this inhibitor is when the non-competitive inhibitor binds to the allosteric site, it changes the tertiary structure of the enzyme. Okay, so it changes the tertiary structure of the enzyme, which in turn changes the shape of the active site. If it changes the shape of the active site, then the active site is no longer complementary to the substrate. And if it's no longer complementary to the substrate, enzyme substrate complexes cannot form. So both of these inhibitors are doing the same thing. They are both preventing the substrate from binding to the active site, but they're doing it in different ways. This inhibitor is doing it by changing the tertiary structure, changing the shape of the active site, which prevents the substrate from binding, whereas our competitive inhibitor, if I go back to this one, is binding to the active site and physically blocking it and physically blocking the substrate from binding to the active site. Okay, so here we've got an inhibitor that's complementary to the active site, binding to the active site and blocking the substrate from binding. Whereas here we've got an inhibitor that is binding to an allosteric site, but it's leading to a change in the tertiary structure of the active site, and that's why the substrate can no longer bind. Both of them are going to reduce the rate of reaction. So finally, and probably the most difficult thing to understand for this topic, is how do we find out experimentally which type of inhibitor we have? Well, the way to do it is to carry out the reaction at increasing substrate concentrations. Because if we increase the substrate concentration and measure the rate of reaction, we can determine which type of inhibitor we have. For example, if we have a competitive inhibitor, when we increase the substrate concentration, which we can see is happening on the x-axis, At very high substrate concentrations, the rate of reaction can reach the same maximum rate as when there is no inhibitor or no inhibitor present. And let me just explain why that is. If you increase the substrate concentration, and we're now at what? Really, really high substrate concentrations here, the substrate is going to outcompete the inhibitor because this is a competitive inhibitor. And if you have a really high concentration of substrate, way more substrate than inhibitor, it's likely that all the enzyme's active sites are going to be occupied by substrate rather than inhibitor. So if you look at the orange line on the graph, you can see that at really high substrate concentrations, the rate of reaction has increased, and it can actually increase to the same maximum rate as if there was no inhibitor present, because the substrate has outcompeted the competitive inhibitor. Now, if we look at the purple line, which is our non-competitive inhibitor, the reason we can tell it's a non-competitive inhibitor is even at very high substrate concentrations on our graph, even at very high substrate concentrations, the rate of reaction is still reduced. It's still going to be a lower rate than if there was no inhibitor present. And the reason for that is no matter how high the concentration of substrate is, it doesn't matter. The inhibitor is not in competition with the substrate. So you could have a super high concentration of substrate and only a very small concentration of inhibitor, but that inhibitor can still bind to the enzyme's allosteric site, and it can still change the shape of the active site, and it can still prevent the substrate from binding. Remember, the non-competitive inhibitor is not competing for the active site. It's not trying to bind to the active site. So even at very high substrate concentrations, the inhibitor is still going to reduce the rate of reaction. So if you're unsure which type of inhibitor it is, you can increase the substrate concentration and look at the effect on the rate of reaction. So if it's a competitive inhibitor, at high substrate concentrations, the rate of reaction will reach the same maximum rate as if there is no inhibitor present. Whereas if it's a non-competitive inhibitor, even at very high substrate concentrations, the rate of reaction will always be reduced. That's probably the hardest thing to understand. But if you just think of the names of the inhibitors, competitive versus non-competitive, yeah? Competitive is in competition with the substrate. So the substrate can outcompete the inhibitor at high concentrations. Non-competitive is not in competition with the substrate. So no matter how high the concentration of substrate, it can still inhibit the enzyme. I hope you found that quick explainer video useful. Do make sure you subscribe and switch on your notifications, because every week we are going to be posting videos which are going to be perfect for Year 12 biologists and also for you Year 13s that need to revise your Year 12 content to help you progress in Year 13.